welcome back. I will continue with this fret because I want you to completely understand. Okay, so let me first talk about with this particular example. In this example, I have two fluorophores, and this is anthracene fluorophore, and this diazo. This is a diazo compound as fluorophore. Okay. So, now this compound we dissolved in solution, and distance between them within 30 angstrom, say 1 to 30 angstrom distance approximately should be. This is within 30 angstrom. We have done the measurement of distance from this value, and that came out to be quite accurate, and that value I do not remember, maybe around 15.5 angstrom, something like that. Okay. So, they are very accurate systems, these things. So, therefore, I have about 1 to 30 from within 30 angstrom, these two fluorophore, and this is important. Absorption spectra of, not absorption, emission spectra of anthracene. Emission spectra of anthracene overlaps with absorption spectra of diazo compound. Emission spectra of anthracene, okay, overlaps. There is a point of this is overlap area, overlaps with the absorption spectra of the diazo fluorophore. Its emission, its absorption. So, it absorbs. In that case, when we excite this fluorophore, it will be excited and then it will emit, but I do not see its emission spectrum. Why? I do not see its emission spectrum, because this emission energy will be completely transferred to the diazo compound, provided the distance between about up to around 30 angstrom and orientation is perfect, or you can say that dipole moment of both should match. Okay. There should not be one is like this, another is like this, orthogonal. No. If they are like this matching, then only there will be transfer. There will be transfer of energy completely to the diazo. So, diazo gets the energy from anthracene. So, anthracene was excited, it emits, it comes down, and energy given to diazo, and is saying whatever you want to do, do. Then diazo is excited because it has got energy, all energy from anthracene. So, diazo is excited, fluorophore. When it comes down, it gives emission spectra of the diazo. So, in this compound, if I was looking for anthracene emission, I will not see at all. Anthracene emission will be like a background, but diazo compound will be a strong emission peak. So, this is called Forster. Earlier it used to call fluorescence. Now, it is Forster is a scientist who did lot of work with this fret. So, now it is called Forster resonance energy transfer, or in short fret. So, fret is a very important technique for biochemists, molecular biologists, very important fluorescence technique to understand the physiology of biosystems. Okay. As I told you, so now I am telling you, I go back to my this one. In this case I told you that there is an active site, and near the active site there is a fluorophore. because natural protein will have any of the three fluorophores amino acid which are fluorophore in nature, fluorophoric, that is phenylalanine, tyrosine and tryptophan. So, suppose this is a tryptophan. Do not ask me what is the emission spectrum of tryptophan, what does it absorb, what does it emit, I forgot. Okay. But what I will see, I will tell you that. So, for tryptophan it is known, okay. It is known, or we can dissolve it and see it, where is the absorption, where is the emission. So, when some work is going on at the active site, suppose active site got something, okay, and it is doing chemical reaction. When it does chemical reaction, there is a lot of changes takes place, in these amino acid. They do this kind of that, they are not fixed, they do this, that, that is why it is so reversible and so efficient. Okay. So, when this tryptophan, when this active site is working, this tryptophan was like this, now it became like this. Okay. Now it became like this, suppose, or all right. So, this is a supposition, suppose they are there. So, what I will do, I put a mutation and put a fluorophore here, fluorophore we supplied. Which fluorophore I will supply? This fluorophore absorption spectrum, will coincide or will have some overlap with the absorption spectrum of this tryptophan. Okay. Then all the energy, emission energy from this fluorophore will be transferred to this particular tryptophan. So, it will be transferred when my tryptophan was this way oriented, okay, then it will be transferred. If it is still like this, okay, dead meat, it is a dead, nothing will happen. When it is like this, means very stable and no reaction is going on here, but some reaction is going on, it is like this because of conformational changes in the backbone, it is like this. So, whenever it is like this, if I excite it, complete energy transfer will take place. So, I will not see emission spectrum of my red fluorophore that I put, but I will see emission spectrum of this natural fluorophore. So, what is the percentage of energy transfer? That will tell us the orientation of this natural fluorophore. It is not the always it will be 100% transfer, maybe 50% transfer. If that is 50% transfer, then I will see 50% my emission here and 50% emission here. So, then I will say that the orientation is not perfect, but maybe some angle like that. Okay, that we can design some compound and come to the conclusion. Okay. So, by this technique you can know what is going on at the active site, and proteins active site some work is going on or some chemical reaction is going on, that will give you the idea of the physiology of that biosystem, maybe a physiology of my physiology. Okay. So, if they put a particular fluorophore, if this is tryptophan, if this is phenylalanine, then I have to see where the phenylalanine absorb and where it emits. Then where it absorb, I have to choose a fluorophore whose emission will match with the absorption spectra of phenylalanine. In that case, my fluorophore will be a different one, not this one, but it will be maybe a green one. It is a different fluorophore. Say different fluorophore. Understand? So, this way FRET, and you know that fluorescence is very sensitive, very sensitive, very quite accurate. So, therefore, from this FRET I would be knowing the physiology of that biosystem. Okay. So, this will actually monitoring what is happening inside me. It can be monitored by equipment, okay, by looking at the emission efficiency of this fluorophore. If the fluorophore is perfectly aligned, because this is, I know the alignment of this. So, if I know the alignment of that also and it 100% transfer, then I will say that this alignment is this way. So, this alignment must be this way, because it is 100% transfer. All right. Then I will see another part. Okay. This is really fun. So, the electronically what we write is this one. Another experiment we will write. Let me write this. This is fluorophore. I am writing fluorophore, fluorophore 1, fluorophore 2, fluorophore 3. This will be, we can call it donor. This is the energy level, okay. Donor, and this is transmitter. It transmits. Transmitter, and this is acceptor. It accepts the energy. Okay. So, what will happen? If I excite, there are 2 electrons. If I excite, one will be up, and then if there is matching, overlap, that is emission matches with absorption of this, then what will happen? It will come here. It will come here, but now there is also matching between 2 and 3. Therefore, it will from transmitter will come here, and this will give you emission. So, I excited this, but I found emission from here. So, this is very interesting. Let me write a system which will show you, we have done some work on this, and I am showing you our that is why I am always showing you this scriptand. With any system you can do. We have taken several systems and did that, but here it is easily available with us, and here in this note also this is there. So, I am trying, does not mean that this is the only one. Okay. Okay. So, now this is also possible because we can one after another I can do. Okay. Okay. And then anthracene. Okay. And then diazo. Okay. Why we have chosen these three? 1, 2 and 3. 3 different fluorophores we have chosen following this, okay, in dissolved in solution. Now, what is happening? I excite this, I only excite this, and what emits? This one emits. Okay. It is very interesting that you excite this one, say this one can be excited around 300 nanometer, okay, around 300 nanometer, and it will emit at 600 nanometer. Why? Because when I excite it, then its excitation, then its emission band matches with the overlaps with the absorption band of anthracene. So, therefore, energy is completely transferred to anthracene. Okay. Remember, all these things work only in solution phase. Solution phase at room temperature, fine, in solution. Okay. So, when I excite this one gets excited because energy is transferred from here. But when this one is excited, it transfer energy to here, and this one now emits. So, this one does not emit, this one does not emit, only this one emits around 600 nanometer. So, it is a beautiful way of saying that. So, this one is transmitter, this one is donor, this one is acceptor. Okay. And this will take place when I have a metal ion here, because metal ion acts as a connector. Otherwise, if I excite it, there will be PET. So, in presence of say zinc or any metal, zinc, okay, I excite it, I excite this one, but I get emission from here, no emission from here or here, because the energy is completely transferred to here and energy is completely transferred to here in solution phase, and they have all single bond. So, they can rotate and get the orientation proper themselves in solution phase. So, that energy can be transferred 100%. All right. I will tell you another picture that also we did. Okay, let me draw here now. Same thing, this one, cartoon. Okay. Basically, once we got them, we started playing with this. have fun. Okay. Okay. So, this then same thing, this fluorophore again okay, 2 of these, and then here anthracene, and then again so we see here diazole. Okay. And then here also. Okay. NO2. So, this compound, so this is also 1, 2 and 3. So, it goes a long range fret. It is a long range fret. I excite it, I see emission from here. So, when I excite it, all energy will be transferred from here to here, and all energy will be transferred from here to here. So, when I excite it, this is excited, and we see a very significant amount of emission and no emission from here or here. So, long range. So, therefore, we were trying to make 5 different. You can imagine that you can make a different one. Play with it. F1, F2, okay, let it be this, then F3, this is F3, this is F4, F5. So, you can see F1 you excite, energy will be transferred to F5, and if this one you excite in UV range, you get emission at infrared. So, that way you get infrared light, that is also important. So, there are many importance of this FRET. In biology, this is a very versatile tool. People work day in and day out with this fluorescence technique. So, therefore, when I discussed supramolecular chemistry, let me summarize what I did in supramolecular chemistry of fluorescence in fluorescence sensing. I worked on sensors, we talked about sensors for different metal ions and anions. Okay. There are some sensors for neutral molecules are also there, like glucose. Glucose sensing is important for diabetes and all that. That also sensors are available. So, sensors, okay. And then we did logic gates. Logic gates are important for information processing or chemical computers. Okay. So, these two, then I did, then what I did? Then I did optical nonlinearity, and finally, I did FRET. So, these are few of the items, that I discussed at length. This is so like that. So, you have a supramolecular synthon, you start and then design your system for any of these studies for sensing, logic gate or optical nonlinearity or FRET for different purposes. So, this way supramolecular chemistry goes. Now, after doing this, what will be left in this part supramolecular chemistry 1, I will describe now amphifiles. Okay. So, this is up to that. Another use that I give, so I want to be ahead in terms of uses. So, that in supramolecular chemistry 2, when I take up, I will always having some more time. Okay. So, I will do synthetic amphifiles. Synthetic amphifiles. Okay. What is an amphiphile? Amphiphile basic structure is like this. This is an amphiphile, means a head group, this is called a head group. And this is called a tail. This will be hydrophilic, and this will be hydrophobic. So, this is a synthesis of So, this can be synthesized. I will talk about this kind of molecules now and what can you do. So, this is also another important supramolecular synthon, this amphiphils. Amphiphils also known as surfactants. Surfactants means surface active agents. Okay. So, this is I just introduce you today. So, from next day onwards I will be doing synthetic amphiphils or what is also called surfactant. Surfactant means surface active. So, this way we will let us start some few lectures. Thank you very much.